In the last lecture, we discussed the properties of Z transform. So in this lecture, let us consider a simple example problems by using the properties. Okay, by using these properties. Let us consider the sequence x of n. X of n is equal to r to the n sin n omega naught times u of n. Okay, now I would like to find the Z transform of this. So you can do it in two ways. Straight away you can write down the formula x of n times r z to the minus n, where n goes from minus infinity to plus infinity. You can substitute, but that is a tedious method. But what we are going to do is, to find the Z transform of this, do the following. Take this sequence x of n and write it in the following form. Sin n omega naught, use Euler's identity and write in this form r to the n e to the j n omega naught minus e to the minus j n omega naught divided by 2j and then multiply by u of n. Then this is r to the n e to the j n omega naught by 2j u of n minus r to the n e to the j n omega naught divided by 2j u of n. Now I have summation of two sequences, and this sequence we know how to find the Z transform. Very easy, right? We know the standard formula and you can use the formula and find the answer, right? We can calculate the Z transform of this easily. You can calculate the Z transform of this very easily. That is, we can sum this up. This is how we can find the Z transform of a given sequence using the properties. Here we are using linearity property. Okay. Here let's say alpha is equal to 1 and here beta is equal to minus 1. And this one is g of n and this one is h of n, like that. And one more important point is this r to the n e to the j n omega divided by 2j u of n is the complex conjugate of r to the n e to the minus j n omega divided by 2j, or I can say 1 by 2j you can take commonly outside, then r to the n e to the j n omega naught minus r to the n e to the minus j n omega naught. See, this r to the n is a real quantity, so even if you take complex conjugate, nothing will happen. This is also a real quantity. But e to the j n omega naught is the complex conjugate of this guy. In other words, we could write this as this is v of n, let me call, and this one is v conjugate of n. The Z transform of v of n is v of z, and this Z transform of this guy is going to be v conjugate of z conjugate, right? So this I can write as 1 by 2j r to the n, because it is complex, v of n plus v conjugate of n multiply by u of n. I can write like this. Now if you apply the formula, then my desired transform, let's say x of z, is very simple, right? This x of z would be 1 by 2j times, okay, v of n. This v of n leads to v of z plus minus, because there is a minus symbol, I forgot here, minus v. So this is minus v conjugate of n leads to capital V conjugate of z conjugate. So no need to find the Z transform of these two guys separately, okay, this guy one more time and this guy one more time. You just to find the Z transform of this and then take the complex conjugate, add them up, that's all. Your job is very simple. Okay, therefore V of Z is the transform of what? E to the j n omega. Okay, times r to the n. Now r to the n e to the j n omega naught, you can easily find out the Z transform. What is the Z transform? We know the formula. Alpha to the n u of n is 1 by 1 minus alpha times z to the minus 1. Now instead of alpha to the n, I have r to the n e to the j n omega naught u of n. Therefore, replace this alpha divided by alpha by r e to the j omega naught times z to the minus 1. Okay, if you have, or else to avoid the confusion, let me write down something else. Let's say a to the n, and here also a. So instead of a, I have r e j r power n e to the j n omega naught. So therefore this guy comes here. That's all. Okay, this I can write r e to the j omega whole to the n. So instead of a, I have r times e to the j omega naught. That j omega r e to the j omega naught is coming over here. Therefore here 1 by 2j, this is 1 divided by 1 minus r e to the j omega naught z inverse minus the same quantity 1 divided by 1 minus r e to the minus j omega naught z inverse, but take the complex conjugate. That's all. So this is 1 by 2j, then 1 divided by 1 minus r e to the j omega naught z to the minus 1 minus 1 divided by 1 minus, anyway r is a complex number, no problem. This e to the minus j omega naught becomes plus j omega naught, and z inverse conjugate. Okay, z is conjugated and the whole thing is also conjugated. Now you can add these two quantities and get the desired result. Okay, let me write down the final result. And the final result is going to be, if you simplify, then you'll get the following: sin omega naught z to the minus 1 whole divided by 1 minus 2r times cos of omega naught z to the minus 1 plus r square z to the minus 2. Okay, so this is the z transform of r to the n sin n omega naught u of n. So sin n omega naught u of n, cos n omega naught u of n, del of n u of n, right? Sin n omega naught u of n, then cos n omega naught u of n, then del of n u of n alpha to the n. Let me write down a to the n u of n, then e to the j n omega naught. Okay, for these basic sequences, you should be able to write without consulting the table, z transform table. Just like your name and your father's name, how you remember, right? So you have to remember this. So you don't have to turn the pages of the book to find this out. So you have to remember this formula of these basic sequences so that you can you can try to find the answer for any given problem. Now let's take an example of multiple poles. In case if I have multiple poles, how can I find the inverse z transform? Let's say x of z is equal to z to the 4 whole divided by z minus 0.5 whole squared times z minus 0.2 multiplied by z minus 0.6. And the ROC is given. ROC is mod of z is greater than 0.6. Greater than 0.6 means outside of the outermost pole. One pole is located at 0.5, another pole is located at 0.2, and another pole is located at 0.6. Which pole is the farthest pole? 0.6. And the ROC is outside of the farthest pole from the origin. Farthest pole from the origin. So it is outside the outermost pole, right? Therefore this is right sided sequence or causal sequence. That one point is very clear now. Okay, therefore it must be a right sided sequence or causal sequence. Now let us try to find out what is its x of n. So if you recall that what we said is that it's a matter of discipline. We write this rational function in Z inverse. Now the given problem is in terms of Z, the polynomial is in Z. Now we need to write in terms of Z inverse. Okay, so therefore we divided by Z to the 4 both in the numerator and in the denominator. Why do we divide by Z to the 4? Because we know the inverse Z transform of 1 divided by 1 minus A times Z inverse. So always write the polynomial in terms of Z inverse so that you can take the inverse Z transform very comfortably. So divide by Z to the 4 both in the numerator and the denominator. So in the numerator becomes 1, the denominator becomes Z to the minus 4 multiplied by Z minus 0.5 the whole squared, Z minus 0.2 times Z minus 0.6. You take Z to the minus 2 here, Z to the minus 1 here, Z to the minus 1 here, minus 2 here, Z to the minus 1, Z to the minus 1, therefore Z to the minus 4. So this becomes 1 minus 0.5 Z to the minus 2 whole squared, 1 minus 0.2 Z to the minus 1, 1 minus 0.6 Z to the minus 1, that's it. So this is my x of Z. Now you can write this as follows. Follow A divided by 1, is it 1 minus or 1 plus? I don't know. One second, I think I copied it wrongly. One sec. I'm sorry, this is 1 plus 0.6. This also Z plus 0.6. Okay, fine. And here also plus. Okay, now you write A divided by 0.6 Z inverse plus B divided by 1 minus 0.2 Z inverse plus C divided by 1 minus 0.5 Z squared plus D divided by oh my god, I'm sorry, I did a blunder here. Okay, this is not Z square because already there is one more square, right? This square is there, no? Therefore this is Z1 and whole square. I'm sorry, really sorry about that. So therefore this is 1 and this one is 1 minus 0.5 Z inverse whole square. That's it. Sometimes I do make a mistake. Okay, now this is a single pole and this guy also a single pole, and here I have multiple poles. Okay, the pole is repeated 2 times. So finding C is not a problem. Okay, sorry, finding D is not a problem, but C is the problem. Let us see how we can do that. Okay, D is very easy to find out. Similarly, A also you can easily find out, B also you can easily find out. So how will you calculate D? D is equal to 1 minus 0.5 Z to the minus 1 whole square times x of Z, and then evaluate at 0.5 Z inverse is equal to 1. Simply you can find out. Similarly, you can find out A value. How do you find out A? A is equal to 1 plus 0.6 Z inverse multiplied by x of Z. Evaluate this whole expression at 0.6 Z inverse is equal to 1. And B also you can find out in the same manner. B is equal to 1 minus 0.2 Z inverse multiplied by x of Z, and then evaluate at 0.2 Z inverse is equal to 1. So straight away you can do this. So I have done this, okay, and then the results are as follows. And D is equal to 25 by 33, A is equal to 27 by 121, and B is equal to 1 over 9. Okay, and as I said in one of the previous lecture that there is a reason why I have kept them as a fraction. Okay, I did not rounded off some number, so I kept as a fraction. Okay, so I have told you the reason also. The reason is that we do not truncate unless it is absolutely essential, because in implementation we have to truncate anyway. We cannot represent every number exactly, so do not truncate till it is absolutely essential. Keep it in this form, as a fraction form, as it is. Now the next question is, how do you find out the variable c? See, we know now a value we know, b value we know, c value we know, and d value we know, but c value we need to find out. So either you can take the traditional method like differentiate once and substitute the value, that is one way, or the convenient method would be like substitute a value for z. Okay, so I have to write only one equation because only one unknown is there, right? Therefore it's very easy to find without going for differentiation and all those things. Now let us substitute z inverse is equal to infinity, okay, in the above expression. Then x of z would be z to the 4 divided by z minus 0.5 whole squared plus z minus 0.2 times z plus 0.6. Okay, now substitute z inverse is equal to infinity, right? So therefore this is z to the power 4. The denominator you can take here in this z square times z minus 1 minus 0.5 z inverse whole squared times z inverse times 1 minus 0.2 z inverse, and here no z inverse. And then if you take z commonly outside, then z times 1 plus 0.6 z inverse, right? So this z to the power 4 will cancel with z squared, z and z, right? So 1 divided by 1 minus 0.5 z inverse whole squared, 1 minus 0.2 z inverse, 1 plus 0.6 z inverse. Okay. Okay, if I substitute z inverse is equal to infinity, then there will be a problem. Substitute z equal to infinity. So this becomes 1 minus 0.5 divided by z whole squared divided by 1 minus 0.2 divided by z by 1 plus 0.6 divided by z. Now you substitute z is equal to 0 in this expression. So this is 1 divided by 1 minus 0.5 by 0. Oh my god, infinity, I'm sorry, infinity. Z is equal to infinity. Infinity 1 minus 0.5 divided by infinity whole squared, 1 minus 0.2 divided by infinity, 1 plus 0.6 divided by infinity. So this is becomes 0 and this becomes 0 and this becomes 0. So you have 1 divided by 1 times 1 times 1, so this is 1. Therefore x of infinity is equal to 1. Okay, the left hand side is 1. What about the right hand side? I have a divided by, you substitute the same thing for a, b, c, d also. Okay, so x of z I got it. In the left hand side is x of z, that is 1, no problem. What about in this expression? Where is a here? Yeah. In this expression, if you substitute z equal to 0, in this substitute z equal to 0, you will get a. And this leads to b if you substitute z equal to 0. Sorry, z in this expression substitute z is equal to infinity. And here also substitute z is equal to infinity, you will get b. And in this expression, you substitute z is equal to infinity, then you will get a d as it is. And this also will become c. Denominator will disappear. So this term will be 0, this term will be 0, this term will be 0, and this term will be 0. Therefore, the left hand side I have 1, x of infinity is equal to 1. The right hand side, you will get a plus b plus c plus d as it is. D value we got it, we know. B value also we know. A value also we know. C value we don't know. Therefore, c is equal to 1 minus a minus b minus d. And substitute a value, b value and d value, then it is going to be 116 divided by 1089. This is the c value. Okay, nothing cancels. So there is no common factor. So if there are common factors, do cancel, okay. Make it as simple as possible. Now the problem is that of inversion. Therefore, x of z is equal to a value. What is a value? A value is 27 by 121 whole divided by 1 plus 0.6 z inverse plus 1 divided by 9 whole divided by 1 minus 0.2 z inverse. Then 116 divided by 1089 divided by 1 minus 0.5 z inverse plus 25 by 33 divided by 1 minus 0.5 z inverse whole squared. Now as far as the first three terms are concerned, there will be no issues. Straight away you can write the inverse z transform for this guy. Okay, so this is going to be minus 0.6 whole to the n. You put the scaling factor in front of this. 27 by 121 u of n, no problem, plus 1 by 9 0.2 to the n u of n plus 116 divided by 1089 0.5 times to the n u of n, no problem. But the problem is with the last term, because you have the square term here. Okay, so how will you do that? 1 minute. This is okay. Yeah. Okay, now let us try to find the last term, inverse z transform of the last term. Now for this last term, let us look at the general formula, and then the general formula is a to the n u of n. If you take z transform, you will get 1 divided by 1 minus a to the a times z to the minus 1. Now if you multiply by n times a to the n u of n, the corresponding z transform will be minus z times d by dz of 1 divided by 1 minus a times z to the minus 1. Right? Now differentiate this minus z times minus, if you differentiate, I will write down the state of the result. This is going to be 1 second. So if you do this, if you carry out this differentiation, you will get a times z to the minus 1 divided by 1 minus a times z to the minus 1 whole square. But here in the numerator I don't have z. Look at here. In the numerator I don't have z. But here I have z to the minus 1. Somehow I need to remove this guy. Okay. How can I remove it? What we want here is in the numerator I don't have z. Okay, the numerator should be 25 by 37 or some constant, or this I can write as 25 by 33 times 1 divided by 1 minus 0.5 z to the minus 1. So the numerator must be 1, but here in the numerator I have z inverse. That is z inverse, somehow I need to remove it. How can I remove that? Again use the property. That property says g of n, if you take z transform, it is going to be g of z. Then g of n plus 1 becomes what? Z times g of z. So I have z to the minus 1 and plus z. If you multiply these two guys, then it will be 1. Therefore this sequence you advance by 1. Okay, if the z inverse has to go, then the sequence here should be advanced by 1 sample. See, this is advanced by 1 sample. Advanced. Similarly, this also advanced by 1 sample. Advanced by 1 sample to get rid of z to the minus 1. This z to the minus 1. Therefore, you write n plus 1 times a to the n plus 1 u of n. Right? If you take z transform of this, then this is going to be z times a to the z to the minus a times z to the minus 1 divided by 1 minus square. Now this z and that z will get cancelled. So this is equal to a divided by 1 minus a times z to the minus 1 whole square. Fine. Now if you look at, I need a constant, but instead of constant I have some other variable a here. So how can I remove that a? You bring this a to the left hand side. N plus 1 times a to the n plus 1 times u of n. If you take z transform, you will get like this. You bring the a in the left hand side. So this is a to the minus 1 n plus 1 times a to the n plus 1. I'm sorry, this is u of n plus 1, because you should advance both u of n also. So this n becomes n plus 1, this a to the n becomes a to the n plus 1, u of n becomes u of n plus 1. Okay, so and this a inverse and this power will get cancelled. 1 divided by 1 minus a times z inverse whole square. Now again simplify this. N plus 1 a to the n u of n plus 1. This is its z transform is 1 divided by 1 minus a times z inverse whole square. Okay, now what I get is something interesting. Okay, I want you to notice this. And now what is the value of this guy at n is equal to minus 1? It is 0, right? So the sequence does not exist. So this u of n plus 1, u of n plus 1 is the same as u of n. Yes or no? Because u of n will be like this. 0, 1, 2, 3. This is my u of n. And u of n plus 1 is delayed version of, advanced version of 1. When you substitute n is equal to minus 1, then it has value. But n is equal to 0, no, it will not give any value. because u of n plus 1 starts at n is equal to minus 1, right? So it starts at minus 1, 0, 1, 2, 3, u of n plus 1 advanced by 1 unit. But when you put n is equal to minus 1, what is happening in this guy? This guy contributes 0, right? If you substitute n is equal to minus 1, 0. So you are essentially multiplying this guy with a 0. This is 0. Therefore, even though you have the value at n is equal to 1 of due to this guy, but this guy n plus 1 gives 0 value. Therefore, u of n plus 1 times a to the n times u of n plus 1 is the same as n plus 1 times a to the n u of n. Okay, therefore n plus 1 times a to the n u of n has a z transform 1 divided by 1 minus a z to the inverse whole square. So that's how we got the inverse z transform of this guy, 1 divided by 1 minus a times z to the minus 1 whole square. So I have multiple poles. So whenever you have multiple poles, then you should invoke the differentiation property in the z domain or multiplication in the time domain. Therefore, where is the z transform? So this becomes plus 25 by 33. What is that? N plus 1 times a to the n u of n. Am I correct? What is a value? A value is 0.5 here. 0.5 whole to the n u of n. This is x of n, or I can write x of n is equal to 27 by 121 is 0.2231 times minus 0.6 whole to the n plus 1 by 9 is 0.1111. I kept the precision up to 4 digits, okay, and 0.2 whole to the n plus or minus minus, I guess. Why is it minus? Oh my god. It is plus, yes, I wrote wrongly. Plus 0.0918, 0.5 whole to the n due to the single pole, plus 0.7576 times n plus 1 times 0.5 whole to the n. Whole thing is multiplied by u of n. Why? Because it is a causal sequence. So this is the simplest form of the given z transform. Okay, so that's it. Now let me prove one more property, or state one more property, that is the last property in the z transform. So to prove that property, let's go back to the modulation theory. So what is your modulation theory says? G of n multiplied by h of n. The z transform is 1 by 2 pi j contour integral of g of v h of z divided by v, where v is a dummy variable, okay, v times v inverse and dv, because already I have z, that's why we introduced this dummy variable v here. So this I am going by the definition. So in this expression, if I make g of n is equal to h of n, and let g of n is equal to h of n and make small z is equal to 1. Then the left hand side simply becomes, I'm sorry, here I forgot to put the summation, n is equal to minus infinity to plus infinity. Summation of n is equal to minus infinity to plus infinity, g square of n, the right hand side 1 by 2 pi j contour integral of g of v times g of 1 by v to the minus 1 dv. Here capital H of z is the same as capital G of v, and here v is the dummy variable. So we can as well change it to z now. Previously I have two variables, one is z and another one is v. Now in this integration I have only one variable. So after all, this v is a dummy variable, I can change v to z, nothing is wrong in that. Therefore 1 by 2 pi j contour integral of g of z, because I assumed z equal to 1, so that variable has disappeared. G of 1 by z and z to the minus 1 and dz. Now if the ROC includes a unit circle, if it includes unit circle, what does it mean? We know that z is equal to r times e to the j omega. On the unit circle, the radius is 1. So therefore this r becomes 1, so z is equal to e to the j omega. Okay, then we know when the ROC includes unit circle, what does it mean? Unit circle, that means DTFT exists, discrete time Fourier transform exists, otherwise the discrete time Fourier transform will not exist. In other words, the contour C can be the unit circle. Okay, the C can be unit circle, so you do the integration on the unit circle. So if discrete time Fourier transform of g of n exists, then we could replace this small z by e to the j omega. That is, if the ROC includes the unit circle, then as well we can replace the contour by unit circle. Agreed? So, and on the unit circle, small z is equal to e to the j omega, and it doesn't take long. Okay, it doesn't take too long to show that the right hand side integral is equal to 1 by 2 pi j integral of minus pi to plus pi. G of z becomes e to the j omega times g of 1 over e to the j omega, and then this dz becomes j times d omega. And this j and that j will get cancelled. Therefore 1 by 2 pi integral of minus pi to plus pi g of e to the j omega, g of e to the minus j omega, and then d omega. This I can say 1 by 2 pi minus pi to plus pi g of e to the j omega mod square, because both are complex conjugate of each other. So one more point I want to mention here is that one of the sufficient conditions for the existence of discrete time Fourier transform is that g of n is absolutely summable. So if g of n is absolutely summable, or in general if DTFT exists, discrete time Fourier transform exists, then my summation, this g square of n, should be equal to 1 by 2 pi times integral of minus pi to plus pi, and then mod of e to the j omega, square of modulus of e to the j omega times d omega. So that means you go round the circle. Okay, we go from minus pi to plus pi. Okay, so what you do is you substitute from this expression you substitute z equal to e to the j omega, then dz equal to, I can simply put in dz is equal to j times e to the j omega and dz by d omega. Therefore dz is equal to j times e to the j omega times d omega. So dz by e to the j omega is equal to j d omega. E to the j omega is z, therefore dz by z is equal to j times d omega, then z inverse dz equal to j times d omega. Therefore this z inverse dz is simply can write j times d omega. That's what we did here. Look at here and this and that. Okay, z inverse dz is replaced by j times d omega, and this j will get cancelled, 1 by 2 pi. And how did you get this limit? It's simple, okay, because you are doing the integration on the circle of unit radius. Now this one is known by the name of Parseval's theorem or Parseval's relation. Therefore Parseval's relation is a consequence of the modulation theorem of Z transform. Consequence of the modulation theorem Z transform. It has to be right. However, I must caution you that there are no sequences for which DTFT exists, but the Z transform does not exist. Okay, there are certain sequences, and vice versa. If the DTFT does not exist, then we cannot apply Parseval's theorem. However, you can apply the general modulation theorem in Z transform. Okay, the statement is very, very important, right? So there are certain sequences for which DTFT exists, but Z transform does not exist. Okay. If the DTFT does not exist, then we cannot apply the Parseval's theorem. So to apply the Parseval's theorem, then for the corresponding sequence, you will be able to find out the discrete time Fourier transform. However, there are certain sequences, even though you are unable to find the DTFT, but you can apply the general modulation theorem. So general modulation theorem is different. General modulation theorem says you multiply two sequences and the corresponding thing in the frequency domain. And here we assume that g of n is real and h of n also real. In case if g of n and h of n both are not real, then what will happen? You take, if it is complex, then you would have taken g conjugate of n, and the same result you would have got it. Okay, so let me stop at this point. So till now we talked about signals, how do they interact now with the systems. That's what we need to find out. Okay, so how the systems will interact with the systems. Therefore in the next lecture we take a discrete time systems and see how it can be characterized in terms of the characterized in the transform domain, how the system is characterized in the frequency domain, how the signal interact with the discrete time systems or digital systems. So let me stop here. Thank you very much.